Hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last session, we discussed about shear of open section beams which are subjected to booms and then which are subjected to different shear loads, and we tried to calculate the shear flow in open section beams by considering the idealization. Now we are extending an analysis of open section beams to the closed section beams, and the learning outcomes in this module are students are able to analyze shear of closed section beams by considering the idealization and probably solve problems on this shear of closed section beams. So this is a formula which we are going to use, and as we discussed in the previous session, that is from here to here, it is a formula for open section beams, that is we represent it by QB, and this is the additional constant shear flow. QS naught is nothing but additional constant shear flow, and that will add for the open section shear flow. Okay, so now this is the closed section shear flow problem. So as we discussed in the previous session, that to solve the problems on this closed section beam, we need to make a cut somewhere in the section and then calculate the rest of the open section. That means, for example, if you have a section like this, so we need to make a cut somewhere so that the rest of the panel of this length becomes open. Okay, but usually it is not a cut section, it is not an open section. But what we are doing to solve this particular closed section problem, we are assuming that we are making a cut here and try to calculate the rest of the open section shear flow problem. And then what we are doing here, we need to take moment summation of all the moments about a suitable point and make it equal to 0. Then from here we are going to calculate QS naught, that's additional constant shear flow. Once you get this QS naught value, and we are going to add it for all the open section shear flow. So QB plus, when you try to add QS naught, for example QB 12, you add QS naught, then QB 23, you add QS naught, then it's going to give the actual shear flow, closed section shear flow, that is Q12, Q23, and so on for the number of panels. Okay, so that is how we do the procedure. So let's see this by considering one problem. So let's consider a thin walled single cell beam which is shown in figure, and that has been idealized into a combination of direct stress carrying booms and shear stress only carrying walls. If the section supports a vertical shear load of 10 kN acting in a vertical plane through booms 3 and 6. So he has given 10 kN vertical load SY. It is acting through the line of action of 3 and 6, booms 3 and 6, and he is asking to calculate the distribution of shear flow around the section. And he has given the boom areas B1 and B8 as 200 mm square, that is because of symmetry. B1 and B8 are 200, and B2 and B7 he has given us 250, and B3 and B6 he has given us 400 mm square, and B4 and B5 he has given us 100 mm square, and he is going to asking to calculate the shear flow distribution. Okay, so that is what the question, and by looking at the diagram clearly you can see that, and it is a closed section, okay, and of having 8 number of booms. So there are 8 booms that are there here for this thin walled single cell beam, and in which again the SY is the vertical load that is considered. Clearly from before we go into the formula, clearly by looking at this diagram we can draw to one conclusion that the given figure is symmetrical about horizontal axis of axis, and so that you can consider IXY, the product of inertia, as 0, and since the vertical shear load is given, you can assume horizontal shear load is also 0. So because of these two values, the first part in the shear flow distribution formula becomes 0, and in the second part we left with only 2, that is minus SY by IXX is only left, summation BR YR, plus we need to add QS naught for this. So this is how the formula reduces. So if you try to look at into this one, because of symmetry, IXY becomes 0, SX is also not given, becomes 0. So completely it becomes 0. This is not required because he not mentioned that shear, that is skin is also taking the direct stresses. So skin is effective only in shear, so that you can substitute this also 0. and again here ix into ixy is 0, this is 0, and therefore in this iyy gets cancelled, so you left with minus sy by ixx summation bryr plus qs naught. So these three you have to consider from this, and then it will be rewritten. So therefore you are going to get this as qs is equals to minus sy by ixx summation r equals to 1 to n bryr plus qs naught. You can consider this as equation number 1. Okay, so clearly by looking at this formula, sy is given to us, and you need to calculate the moment of inertia for the section. Now how to calculate moment of inertia for the section? Let's try to see here. So since it is symmetrical about horizontal axis, you need to consider the moment of inertia either above or below of this horizontal axis, so that you can multiply by 2 to get the moment of inertia for the complete section. So let's try to write the formula for moment of inertia, which we know is nothing but when the booms are present, ixx equals to summation br yr square. Okay, so ixx, that is equals to, let's try to write for 1, boom area for 1, that is nothing but equals to 200, and its y distance from the centroidal axis from here to here, which is nothing but 30. So we'll write 30 square, plus coming to boom 2 area is nothing but 250 into its y distance from here to here, it is nothing but half of this, that is 100. So 100 square plus boom 3, that is nothing but area is 400. So 400 into its distance from here to here, it is again 100, that is you have to write 100 square, plus boom 4, that is area is 100 into its y distance from here to here, it is 50. So 50 square. So this is on the top of the, above the horizontal axis. So you have to multiply by 2 to get for the complete section. And if you do so, you are going to get moment of inertia. Okay. So you will get moment of inertia as 13.86 into 10 to the power of 6 mm power 4. And let's try to substitute in place of ixx, and also let's try to substitute the sy also. So minus sy is nothing but 10 kilonewton, 10 into 10 to the power of 3 divided by ixx, 13.86 into 10 to the power of 6 summation bryr plus qs naught. And if you try to solve this one, you are going to get qs equals to minus 7.22 into 10 to the power of minus 4 summation bryr r equal to 1 to n plus qs naught. So this is the sequent equation that you need to consider. Okay, so up to now here we've used the formula, we try to calculate ixx and we substituted for sy, and then we got the qs, the shear flow distribution. Now you need to look into this one, and qs naught is there because it is a closed section. Up to here it is a open section qb, and this is a closed, qs naught is added because it is given for the closed section, additional constant shear flow. Now as we discussed, to extend our problem from here, then you need to make a cut somewhere and then assume in any of the panel, because here there are 8 panels, 1 2 3 4 5 6 7 8. Any panel we can make cut. For example, if you try to cut in panel 1.8, then you can assume the shear flow in panel 1.8 must be 0. Then you calculate the rest of shear flow followed by QB12, QB23 and QB34 and so on. Okay, so that is all the procedure, and after that you have to take the moment about a suitable point. Okay, so let's see in this one, and let's assume that you are making a cut in wall 2-3, cutting the wall in 2-3 and calculating the rest of the shear flows. So I thought that I am making a cut in wall 1.8, but he considered that he is cutting the wall in 2-3. So that is what I mentioned. Out of 8 walls, you can make cut anywhere and calculate the rest of the shear flow, open section shear flow distribution. So since here he mentioned QB23, he made a cut in 2-3 wall, then you have to start finding to calculate 3-4, 4-5 and 5-6 and so on. Okay, so that is how the procedure will be. So now if you look at into this one, so QB23 is assumed, that is it is taken as 0. It is not actually 0, but we have made a cut and we are assuming it as 0. And next shear flow, that is QB34, formula is minus 7.22 into 10 to the power of minus 4 BRYR. So you have to substitute the boom area of 3 and its respective y distance. So if you look at the boom area for 3, it is 400 and its respective y distance of boom 3 from the central axis is nothing but 100. okay, half of this one. So you have to substitute 400 into plus 100. So 400 into 100. So 400 into 100. So you got minus 28.9 Newton per mm. Similarly, the next shear flow for 4-5 you have to consider. So next shear flow also minus 7.22 into 10 power minus 4. You have to look for the boom area 4 and its respective y distance. So if you look at the diagram, boom area 4 is nothing but 100 and its y distance from the central axis from here to here it is 50 mm, half of this value. So 100 into 50 is the boom area into y distance corresponding to boom 4. So that you have to add here 100 into 50. But for 4-5, then you need to understand one more thing. You made a cut here and you assume that shear flow in this wall is 0. So that you calculated 3-4. Now while you calculate 4-5, there is a starting shear flow. For 4-5, the starting shear flow would be 4-3. That you have to add to this 4-5. Okay, that you should not forget. Similarly, when you are trying to calculate for 5-6, you have to add the shear flow of 4-5. That will be the starting shear flow. Okay, only for the first one, the QS naught is 0. That's why we don't consider, because it is an open section. In the formula also you can see everywhere there will be QS naught. Okay, for the starting panel, this we have assumed QB23 as 0. Then we got only this. For the next one, you need to consider. So therefore, for QB45, the starting shear flow would be QB34, and that what we got is minus 28.9 that we have to add for this. Okay, when you do that, you are going to get minus 32.5. Okay, and coming to the 5-6, QB56 is equal to QB34 by symmetry. So you can look at this one. QB56 is almost equal to 34 from symmetry. So that is what it is written here, and minus 28.9 Newton per mm square. And QB67 and QB23 are considered as 0 because we've already assumed QB23 as 0. So you can consider QB67 is also 0 because of by symmetry. Okay. Now trying to calculate the other one, that is 2118 and 87. So 2118 and 87. So again here if you try to calculate QB21, again minus 7.22 into 10 to the power of minus 4 is the shear flow, and you have to look for the boom 2 area and its y distance from the centroid. Boom 2 area is nothing but 250 and its y distance from the centroid is this much, that is nothing but half of this 200, that is 100. Okay, and the starting shear flow for 2-1 would be what? 2-3. Okay, but that is already 0, so no need to consider that. Okay, and when you do that, you are going to get the QB21 as minus 18.1 Newton per mm. Now similarly, let's try to write the next one also, that is QB18. So QB18 will write as it is minus 7.22 into 10 to the power of minus 4 into, you have to look for the boom area 1 and its respective y distance. So boom area 1 is nothing but 200 mm square, and the respective y distance of boom 1 from here to here it is half of this value, that is 30 mm. Okay, now for which for 1-8 the starting shear flow would be 1-2, that you have to add. So 1-2 we got minus 18.1 Newton per mm. So that 1-2 you have to add as it is, that is minus 18.1. Okay, so in this way you are going to get QB18. Now how much we got that? The QB18 is nothing but you got minus 22.4. Okay, so here you can write minus 22.4 Newton per mm. That is nothing but what? QB18. And again QB87 is almost similar to 2-1 by symmetry. So you can write QB21 and then you can write that is same as minus 18.1 Newton per mm. Okay, so this is how we try to calculate the open section shear flows. Remember, these are not the actual shear flows. These are all the open section shear flows we calculated by making a cut in panel 2-3, and we are assumed it as 0 and then we calculated this. But in the actual practice, even the wall 2-3 is also not 0. It is a closed section, right? If you look at the diagram here, even wall 2-3 is also closed. That means if you don't make a cut, here there would have been some shear flow in this wall also. And we are assuming that as QS0, additional constant shear flow, that would have been existed in wall 2-3 if the cut is not made. Okay, now we are going to predict what is that shear flow that would have been there in panel 2-3. Okay, so Now after calculating all this, now what we are doing here, it is taking moments about the intersection of the line of action of the shear load and the horizontal axis of symmetry referring to the axis. So where we are taking the moment? We are taking moment about the line of action of the vertical load and the horizontal axis of symmetry. That means you are taking moment about this point. Let's consider this point as O. So you are taking summation of all the moments about point O and must be equal to 0. And when it comes to the summation of all the moments, so first thing is moment due to shear load, and then the second one is moment due to all the shear flows. So we got the shear flow, here it is 0, and let's try to draw here. Yeah, so here it is 1, 2, 3, 4, 5, 6, 7 and 8, and this you got minus 18.1, this you got minus 18.1, and then QB34, this is 0 anyway, that we assumed, and this is minus 28.9, and the next one is minus 32.5, and the next one is 0. This is also same, minus 28.9, and this is 0. So these were the shear flows we got. Okay. So these are the shear flows what we got, and in the respective manner. And now there is already again one more, that is 10 kilonewton load is also there, and you are going to consider the moment about this point. Okay, and then plus you have to add additional constant shear flow. That is very, very important. Okay, what is the additional constant shear flow? So that is QS not everywhere, and this we got negative, so that you can write this direction. Okay, and this 0 anyway, and this is minus. Okay, so this is additional constant shear flow. So this additional constant shear flow we have to add to this open section shear flow to get the actual shear flow. So that now we are trying to consider the moment about this particular O axis, and again here also this particular O axis. So two diagrams we need to consider. First, let's try to write the moment due to the first diagram. The first diagram here you can see here QB1 QB81. So QB81, this is 8, and this is QB81, and how much we got the shear flow for this is minus 22.4. Okay, 22.4. Now this, let's try to consider this minus 22.4. Okay, and now let's try to write this one. So QB81 is the shear flow that you got like this, and QB81 into its length is nothing but 60, and its perpendicular distance from here to here, it is nothing but 480. Okay, so shear flow multiplied with its length and then multiplied with the perpendicular distance. So shear flow, when it is multiplied with the length, it becomes force, and the perpendicular distance when you add, it is going to become 480. Okay, so QB81 into 60 into 480, now this becomes the moment. Okay, and similarly for the next one, what we are doing here for 1, 2, what I am trying to do here, it is, so I am going to apply the formula that is equals to 2AQ, that is 2 into area into Q, that is the torsional moment, and that we are going to apply. So when I try to use this moment, so 2 is the 2, and then Q is nothing but QB12, and then what I am trying to do here, it is, so I am going to consider, since I am going to calculate the moment about point O, I have to join like this and try to calculate this area. Okay, so this area from the simple geometry you can calculate, and it gives 240 into 100 plus 70 into 240. So that you can see, you can consider from the geometry of the diagram, you are going to get that area. Now when it comes to the next one, that is QB23, so 2 into QB into 23, this length is nothing but 240, and this distance, perpendicular distance, is 100, and next one is minus 2Q, that is minus, and this we will got because now from here 2 into QB43 into 120 into 100 is nothing but this distance and this length, and this is the perpendicular distance what we get. And then coming to the next one, QB54, and minus QB54 into 100 into 120, that you can add. So that you're going to get all the shear flows, that is the moment due to shear flow we have written. Okay, so up to now here it is for the first diagram, that is the moment due to shear flow. So this formula is very simple, that the shear flow must be multiplied with its length first, then it will be converted into force, and then you have to write the perpendicular distance from the line of action of that shear flow to the point where we are calculating the moment, that is the perpendicular distance. Then it becomes the moment. Now coming to this one, this is the clockwise moment we considered, and for this also you have to apply 2AQ, that is a torsional moment, that is 2AQ S0. So 2 into area of this particular complete cell, which comes as 97,200 when you calculate, into QS0. Okay, and when you try to do this, you are going to get QS0 is equal to minus 5.4 Newton per mm. So this is the additional constant shear flow that would have been there in this panel, that has minus 5.4 Newton per mm. That is 2-3, panel 2-3. Now once we get this QS0 as minus 5.4 Newton per mm, then we have to add to all these shear flows. Okay, so how to add this? For example, Q21, 2-3 we got minus 0.4, so you can represent this in the similar direction, that is minus 5.4. Okay, and 2-1 we calculated like this in this direction, in fact. So when you try to calculate this one, and the direction, when you try to represent at 1-2, I am trying to represent this one. So this is 18.1 minus 18.1 we got, and this is superimpose that onto this one, so this is minus 5.4. and when you try to put it in this one in the reverse direction, so this is a major direction, so minus 18.1, and this minus 5.4, if you try to reverse the direction, then it will become plus 5.4. so the total, this is 1, 2, so the total shear flow at this panel would be minus 12.7 Newton per mm. So that is how. So once we get the QS0 value, we have to superimpose onto the existing diagram, so to get the actual values. So Q21 we got minus 12.7, which is equals to Q87, and Q23 we got minus 5.4, which is equal to Q67. So similarly you have to write the other one also. So Q34 equals to Q56, that is equals to minus 34.3 Newton per mm, and Q45 minus 37 Newton per mm. And because why? Because here if you look into this diagram, and for minus 32.5 minus 27.5, this is going to add, because if you look at the directions, so this is in the same direction, 32.5, this is 28 point is also there in the same direction, this 5.4 also is in the same direction. So minus 32.5 is going to add minus 5.4, and for minus 28.9 it is going to add for 5.6 minus 5.4. So it's going to add, so you're going to get 3.4 as minus 34.3 and 4.5 as minus 37.9. Similarly for 8.1, so 8.1 again it's going to subtract minus 18.4 plus 5.4 you can apply, and here also for 1.8 also you can apply plus 5.4 plus 5.4 here, then you are going to get Q81 as 17 Newton per mm. So these are the actual shear flows what we get. Okay, so this is how the closed section shear flow procedure will be there, and you have to do it with utmost care, and even the calculations also you have to do very carefully, because even one small mistake if you make, and it's going to lead for wrong answers. So you have to be very careful for calculating the actual shear flow for this closed section beam. And once you get this actual shear flow, you have to represent in this diagram like this one. Okay, for example, Q81 is positive, you got 17, so positive, the direction you can take 17, and Q12 also positive, so you can take this direction, and here Q23 is negative, so you can reverse the direction. Okay, this is also negative, so you can reverse the direction, negative, reverse the direction, negative, reverse the direction, negative, reverse the direction, positive in the same direction. So like that, the actual shear flow must be drawn once you find all the closed section shear flow. Okay, so that's all from today's class of shear of closed section beam subjected to shear loads and calculation of shear flows for the closed section beam. Okay, so in the next class we'll discuss about torsion of beams which are subjected to structural idealization. So that's all for today's session, and in the next session we'll be discussing about deflection of open and closed section beams, and we'll try to find out how the deflection is calculated for open section beams and closed section beams. Okay, so thank you everyone.